Hello friends. So today in continuation with previous video, we are going to talk about mechanism of load transfer in RE walls, reinforced earth wall. So how from overburden, from surcharge, the load gets transferred to the reinforcing element such as geogrid and how the tension gets developed. So load transfer mechanism is very important. So today we'll be talking about load transfer mechanism in a reinforced earth wall. So as you see, there is the facial panel. There is the pad and there is the fill material. And to this facial panel, we are going to connect it with the reinforcement. Reinforcing element is geosynthetics, maybe geogrid. So let's say this is the geogrid. This is then another layer. This is the geogrid. This is the geogrid. Third layer. Fourth layer. This is the fifth layer. This is the sixth layer. This is the seventh layer. This is the eighth layer. So this is called RE wall. This is the backfill. And these are the reinforcing element or reinforcement, which is going to be, let's say, geogrid. Is connected to the facial panel. And here, the properties of the wall fill, this is the RE wall. So this RE wall has got properties, fill material, wall fill. Let's say its unit weight is gamma r. The angle of internal friction is phi r and C equal to 0. Now, I have already explained to you that the failure pattern is as per Rankine's theory. So there is the slip surface. And the slip surface or slip plane is inclined with the horizontal at an angle of 45 plus 5 by 2. That you know it. Now, due to this wall fill material, what is the vertical pressure? The vertical pressure here is due to overburden, isn't it? The vertical pressure is due to overburden. And if there is a surcharge, let's say you have a surcharge. and this surcharge is Q. Then this is due to overburden. This will be equal to gamma R into Z at any depth. Z, isn't it? The vertical pressure. And due to overburden, due to surcharge Q, surcharge, uniform surcharge is there. What is the horizontal pressure or vertical pressure is Q. So what is the horizontal pressure? Total horizontal pressure, we can call it PHR in the reinforced zone, is going to be gamma Ka in the reinforced zone multiplied by gamma R into Z due to overburden plus surcharge. This will give you the horizontal pressure. So you can calculate the horizontal pressure where K in the wall fill material, that is the reinforced zone, can be found out from famous expression 1 minus sine phi r upon 1 plus sine phi r, where phi r is the angle of internal friction in the reinforced zone. So very easy way we know this. And what is the spacing between, this is the layer 1, this is the second layer, this is the third layer of geogrid, fourth, fifth, sixth, seventh, total 8 layers. So this is the vertical spacing, right? So if you know the vertical spacing, so due to the fill material, there is going to be proper bonding between the geogrid and the soil mass. So from this center point and this center point, if you take it, this is also going to be the vertical spacing. So this geogrid is bonded due to overburden and due to surcharge, and the horizontal pressure that is being transferred to the reinforcement will be equal to PHR equal to K gamma RZ plus Q. So what is the tension that is getting developed over here in the reinforcement? So in the reinforcing element, the tension that is going to get developed, we call it design tension or TD, will be equal to what is the horizontal pressure in the reinforced zone, PHR, multiplied by the vertical spacing, which I have just talked about, divided by a coverage ratio. CR is called coverage ratio. By geogrid, how much ground is being covered, so coverage ratio. TD you know. Therefore, you can calculate the allowable tension. This is design tension or tension developed equal to, given by this expression, and T allowable, if you know the tension that is getting developed multiplied by factor of safety. This factor of safety, you can take it as 1.5 and find out the allowable tension. So what should be the ultimate tensile strength? Of the reinforcing material. Reinforcing material. That is called T ultimate. What should be the ultimate tensile strength of the reinforcing material? Because now you already know the allowable tension in the reinforcement at any depths Z, because PHR is a function of Z. So at any depth Z, as the Z increases, where Z is taken from here in the downward direction, it is going to increase from top to bottom of RE wall. The value of Z will increase. And as Z is going to increase, your horizontal pressure is also going to increase. So the maximum PHR will be at the bottommost point, where Z equal to H, where H is the height of the wall. So from top up to the bottom, this is the height of the wall. So the maximum value of TD, this tension that is getting developed, will be where? At the bottommost point. So this is how the load is getting transferred. And the vertical spacing, whatever vertical spacing, you are going to keep it, and the divided by coverage ratio. If coverage ratio is 1, then it becomes PHR into SV. And then the allowable tension in the reinforcing element is TD into factor of safety. And the ultimate tensile strength of the reinforcement is allowable tensile strength into reduction factor for installation damage, ID. During the installation, you will have to take reduction factor, factor of safety. For installation damage, normally we keep it 1.5 multiplied by reduction factor for creep. This also we keep it 1.5. Then reduction factor due to biological degradation. Your reinforcing element, if it is biodegradable, geosynthetic is non-biodegradable, then you should take the appropriate factor. So reduction factor, you should take it, and the reduction factor for chemical degradation. So chemically, if it is inert, well and good, but some of the chemicals also react with the polymeric material such as Geogrid and geotextiles. So you will have to take some factor of safety. So reduction factor, accordingly, you will have to take it. Let's say I take it these two factors as 1.5, then 1.5 into 1.5 into 1.5, I can find it out, what is the value. So the TA multiplied by those factors, you should multiply it. So if I take 1.5, this becomes 3.375. So I can take it, say I am going to have this biological degradation as 1 and this as 1.5. Then 3.375. This is the reduction factor. 3.375 is the reduction factor. So you can take it. So you can find out the ultimate tensile strength. So friends, this is very important expression that you should remember, and that is how the load is going to be transferred due to surcharge, due to overburden in the wall fill zone. So in the wall fill zone, you can calculate PHR as Ka into gamma R into Z plus Q. And once you calculate this, which is a function of Z, multiplied by the vertical spacing divided by shear. So you are in a position to calculate the ultimate tensile strength of the reinforcing element that you are going to use in a RE walls. For the internal stability, you can see that this zone, that is right side of slip surface, this side, from here up to here, this is known as effective length LE. So I am going to have a effective length LE in the wall fill. So friends, LE equal to effective length of reinforcement, that is Geogrid. I am talking about Geogrid reinforced wall. So LE, and this zone right side of the slip surface, right side of the slip surface is called active zone. Why it is called active zone? Because it contributes to pull-out resistance. Because tension is getting developed in the reinforcement. So if the tension is getting developed in the reinforcement, should not be pulled out. So tension is getting developed. This is the reinforcing element, this is the geogrid, and this is the facial panel. The tension is getting developed. This should not be pulled out. So pull-out resistance will come due to active zone. And this is called non-acting zone, or this left side is called non-acting zone. Why it is called non-acting zone? Because it doesn't contribute to either strength or pull-out resistance. And the length in the non-active zone of the reinforcement is called LR. So this is LR and this is LE. So total length of the reinforcement becomes length in the non-acting zone, that is LR, plus length in the active zone, that is L effective. So that is the total length of the reinforcement. How will you find out LR and LE? Because this angle is 45 plus 5/2. With the vertical, this angle, you can calculate it. This angle with the vertical will be how much? This will be naturally 45 minus 5 R by 2. This is phi R. by 2. So this is the angle. So at any depth z, say at this depth, the jet. So what is the remaining height is h minus z. So LR you can calculate. LR at any depth z. There is the wall, there is the fill, there is the reinforcement. Say at this depth z, and there is the pad, there is the height h. So this height becomes total height minus z, and there is the failure plane. So this LR will be easily calculated as h minus z into tan of this angle, isn't it? So it will be into tan 45 minus phi r by 2. So this is the angle. This is going to be opposite side divided by this. So h minus z. H is known to you. The total height of the wall you are going to construct. Z at any depth you can find it out. Phi r is already known to you. The wall fill internal angle of friction is known to you, and therefore the value of LR at any depth in the non-acting zone, the length of the reinforcement can be calculated from this expression. So this expression is quite useful. LE, LR. Now how will you calculate LE? Now LE is this one from here to here. This is the length in active zone. So as I have shown you. Now what is the total pressure, vertical pressure? The total vertical pressure is sigma V due to overburden plus if there is a surcharge. There is a surcharge. Q. So it will be plus Q. And only due to overburden, it will be sigma V naught. Now, the LE value can be found out from pull-out resistance. The pull-out resistance will be offered by this. The tension is getting developed and the pull-out resistance will be offered by this length. So this will offer a pull-out resistance due to this vertical pressure. So the pull-out resistance is very important. Let's call it as PR, pull-out resistance. So PR will be due to this vertical pressure, and there will be reaction. So on both the surface, this is completely bonded now. So it is going to be sigma V multiplied by tan delta. What is delta? Angle of wall friction. That is due to the fill material here and the friction between, angle of friction between the geosynthetic, that is geogrid, and the granular material is called angle of wall friction. So sigma V into tan delta. Because it is acting at both the surfaces, you multiply it by 2. So this is multiplied by length LE. So this is going to be the length LE, which offers the pull-out resistance. This zone doesn't offer any pull-out resistance. So pull-out resistance comes from LE. So multiplied by LE into what is the interaction coefficient. So Ci multiplied by what is the coverage ratio. So here the formula becomes 2 times Ci interaction coefficient into Cr the coverage ratio multiplied by sigma V tan delta into Le. Now sigma V is a function of Z. This is a function of Z. Right? So at any depth Z, you can find out the vertical pressure and uh, always the condition is that pull-out resistance offered by Le should be more. So pull-out resistance should be greater than or equal to the tension that is developed in the reinforcement. So you have seen that tension is getting developed, and the condition is, this is the condition, that pull-out resistance should be greater than equal to the tension that is getting developed, or tension that is getting developed should be less than equal to the pull-out resistance, which is given by this expression number 3. So pull-out resistance you have seen in expression 1, expression 3, and the tension that is getting developed, you have seen it, PHR into SV divided by CR in equation 1. That must be less than equal to PR. The moment this TD is greater than pull-out resistance, then what will happen? The wall is going to fail in internal stability. Then the stability of wall will be in danger. So this you must take care of. And to find out this LE required length, what we do it is you find out the tension that is getting developed and multiplied with some factor of safety so that it becomes true allowable, must be equal to PR value. So this is how the load is getting transferred in the reinforcing element. It is very, very important and you should know it. Thank you very much.